Once the data is saved on magnetic tape, we can get a hard copy printout of the waveforms for analysis. In addition to the oscillograph machines themselves, there are several accessories that must be installed to complete the recording system. And these include starting sensors or triggers to start the recordings, signal conditioners to prepare the data for recording, power supplies and inverters to provide an uninterruptible power source for the oscillographs, and time clocks to keep track of the exact time of recording. The time log helps coordinate the output from many recorders. The most important accessory is the starting sensor. The sensor is basically a relay which continuously monitors the power system and detects disturbances such as faults and power swings. The sensor signals an oscillograph machine to start recording. Fault sensors are the most common type. Now, they typically respond to overcurrent or under voltage. For example, this overcurrent sensor in the neutral circuit of a transformer detects single line-to-ground faults out on the system. Often this sensor is backed up by a zero-sequence voltage sensor connected across the broken delta winding of a voltage transformer. This measured voltage is zero under normal conditions, but it greatly increases for a line-to-ground fault. Thus, we can set the voltage sensor very sensitively to provide good backup for the current sensor. We can also use a negative sequence voltage sensor connected to the bus. This will sense a phase-to-phase fault on any line connected to the bus. You will remember this phasor diagram from an earlier lesson. It shows the voltage broken down into its positive and negative sequence voltages. Before the fault, we have balanced three-phase voltages. The negative sequence component is zero. As soon as the fault is applied between A and B phases, the negative sequence voltage suddenly increases. So when this sensor detects negative sequence voltage, we can be quite sure that a fault has occurred and recording can begin. Another type of sensor, the disturbance sensor, responds to slower changes in voltage, current, or even system frequency. These slower changes take place over many cycles and are commonly called system swings, instability, or oscillations. Oscillographs do have their limitations. For example, a lightning surge would not be recorded because it's much too fast. A typical current surge due to a lightning strike reaches its peak and decays to zero in a matter of microseconds. Although our conventional recording machines could not pick up the actual surge, we may be able to see the effect of the lightning. This trace shows B phase to neutral voltage on a transmission line during a lightning storm. Look carefully at these points. Here we see the high-frequency effects of arresters operating and conducting surge current to ground. Subsequently, at this point, the high voltage associated with the lightning surge flashed over the line insulators, creating a temporary phase-to-ground fault. You can see the dramatic decrease in voltage due to the fault. This particular recording was started automatically when the fault occurred and captured about 5 cycles of pre-fault data. Because of the pre-fault capability, we can see the effect of the lightning arresters. But take note, the recording would not have started at all if a fault had not subsequently developed. This is because the sensors can only detect longer-term disturbances in the range of milliseconds or seconds. A normal arrestor discharge without a fault is too fast to be picked up by the sensors, so it would not start the recorder. We have been looking at oscillograms associated with faults on the system. Generally, the whole story can be shown within a few cycles, usually less than 1 second. System swings such as those associated with instability, can also be recorded, but such swings may last for several hundreds of cycles and consequently give us a lot of paper to examine. Some oscillographs have the ability to change paper speed automatically when recording these longer-term swings. In recent years, most of the fault analysis systems installed are of the digital type, generally known as digital fault recorders. This type of system usually allows for a greater number of monitoring inputs. The measurement, that is, sampling, is made simultaneously from all inputs, and a very high rate of sampling is achieved, say 6,000 measurements per second. The analog input is converted through an AD converter into a digital signal to be recorded in the memory of the recorder. The information can be viewed on the computer screen or printed out as required. Usually, the screen traces can be compressed or expanded in both time and amplitude so that a variety of signals can be compared. For precise examination, the curves can be overlapped. A distinctive advantage is the capability for immediate remote retrieval. Information from various locations can be brought into a master computer for analysis at a central location. In this context, another advantage is in the precise timekeeping of the digital system. Yet another advantage is the capability to adjust the individual trigger set points from remote central control. In some digital systems, a printout of equipment status can be produced similar to the SER. As further development takes place, it is probable that gathered information will be analyzed instantaneously by the computer and switching operations initiated. Keep your eye open for such developments on your power system. So up to this point, we've discussed what types of oscillograph machines are installed, what sensors start the machines, and what types of disturbances they can record. Now, let's consider where on the power system these machines may be located. Obviously, we cannot locate the recorders at every substation. The cost would be too great. As a general rule, most utilities find that they can adequately monitor the system by installing recording machines at every station in the extra high voltage range, that is 345 kV and above, every other station in the high voltage range, such as 115 kV and 230 kV. This allows at least one end of each high voltage line to be monitored, every major generating station, and every station with interconnections to other systems. Normally, oscillographs are not located at the distribution substations except those installed to analyze special problems or to conduct research. But it is just as important to analyze incidents occurring on the distribution system as on the high voltage power system, even though